So first of all, organic chemistry, always focusing around these organic compounds. And organic compounds necessarily contain what elements? What's the star of organic chemistry here, element-wise? Carbon. And then there's also another important component. So organic compounds necessarily contain carbon and what? What's the other element, non-metal, that we see all over the place? Hydrogens, all right? So organic molecules necessarily contain carbons and hydrogens, all right? And so the first thing that you would have learned how to do is how to represent different organic structures. And that's exactly where we're going to start here as well. Okay, so again, rewinding back to the very beginning of that first semester, you learned how to draw these molecules. Because as you would have noted in the first semester, there's really not a lot of math in this course in comparison to general chemistry. General chemistry, and actually a lot of the chemistries, analytical, physical, all very computational based. Organic chemistry doesn't have a lot of math involved. Instead, we're drawing structures all the time, right? We're manipulating those structures with these chemical reactions. We're talking about properties of molecules based on these structures. It's all about the structures, right? So that's the first thing that we would have learned how to do, is learn how to draw these structures, all right? Importantly, because we are limited to these like set, first two rows of our periodic table, we can just kind of, instead of doing the long way of drawing structures that you learned how to do in general chemistry, we can go ahead and just pay attention to these bonding patterns. We're going to make this little bonding pattern cheat sheet here. Okay, and this tells us how many bonds and lone pairs an element likes to have. All right, and I'll clarify what I mean by likes to have here as we get a little bit further in our lecture. But nonetheless, if you remember back to general chemistry when you were drawing Lewis structures, when you first learned how to draw covalent molecules, you were counting up valence electrons, and you had this whole procedure that you were following. Because we're paying attention to just the first two rows on our periodic table, the smaller elements, we can simplify these rules. All right, so what we're going to do is we're going to create a little chart where we have number of bonds and number of lone pairs. And we're going to list that for each of these elements here. All of our nonmetals that are important in organic chemistry are going to go from smallest to biggest here. So hydrogen, carbon, the two stars of the show, plus these other what we call heteroatoms that we see often, nitrogen, oxygen, and then that halogen fluorine. All right, so these are all nonmetals. They'll form covalent bonds with one another. That's what all the molecules that we look at in organic chemistry are, covalently bonded molecules. All right, so if we're going for our bonding patterns here, hydrogen, being so teeny tiny small, can only have 2 electrons in its valence shell. So hydrogen likes to have just one bond, won't have any lone pairs associated with it. All these other elements are trying to complete their octet, right? So they're trying to get to a total of 8 electrons. Carbon likes to have how many bonds? 4. And that's its 8 electrons, so it won't have any lone pairs. All right, what we're going to see is this trend here. For example, nitrogen, it likes to have 3 bonds and 1 lone pair. So we can see as we're going across our row here, our number of bonds decrease and our number of lone pairs increase. So by this same trend, what would we expect for oxygen? How many bonds and how many lone pairs? 2 bonds and 2 lone pairs. All right, and then fluorine, how many bonds and how many lone pairs? How many bonds? 1. And how many lone pairs? 3. All right, so as we can see, decreasing in our number of bonds, increasing in number of lone pairs as we're going across our periodic table. I do want to note that these bonding patterns are the same for everybody that lives in the same family on our periodic table. So for example, we have fluorine here. This is really true for all of our halogens. And we do see all those halogens quite frequently. Fluorine is actually the least reactive of all the halogens. So we don't see that one very much. Chlorine and bromine we see way more frequently. All right, but they'll have these same bonding patterns. Likewise, oxygen lives in the same family as sulfur, so sulfur has similar bonding patterns. Nitrogen lives in the same family as phosphorus, so phosphorus has similar bonding patterns. Cool, so using just these simple rules here, everybody's going to take a second and draw me a structure. Actually, if you want to be good, we can draw two distinct molecules that have this chemical formula, C2H6O. See if you can't give me both of those molecules. All right, we'll just make it clear. All right, and again, there are two distinct molecules that we can draw that share that same chemical formula. All right, so there's two structures that we can draw. I'm first going to show you what we first learned how to represent our structures with, what are called Lewis structures. All right, the one that I kind of expect that everybody would get first is if we put those carbons, and oxygen all in a row here. Hydrogen, because it only has one bond, will always just decorate the outside of the molecule, right? So you want to put those core atoms in first, those backbone atoms, and then we're just going to decorate, make sure that everybody's happy. So this carbon's going to need 3 hydrogens. This carbon's going to need 2, and oxygen likes to have 2 bonds. And what am I missing here? Those lone pairs. Lone pairs are really important in understanding the chemistry of a molecule. So we're always going to be good and explicitly represent our lone pairs. There was another one that I could draw here. Did anybody else get that second one? No? All right. So first of all, what functional group am I looking at here with this OH? An alcohol. Oops. All right, we can draw also an ether. All right, I want everybody to take a second. Try to remind yourself, what is an ether? How can we draw a 2-carbon ether here? What's the difference between an ether and an alcohol? All right, whereas alcohols have an OH group, so the oxygen is on the end of a molecule. An ether means that our oxygen is in the middle of our molecule, sandwiched between two carbon atoms. All right, so completing our octet here for our carbons, our oxygen already has two bonds. It needs its two lone pairs. So again, this molecule here being an alcohol with its OH group, an ether necessarily has a carbon-oxygen-carbon bond, an internal oxygen there. All right, and this is a good example of why these chemical formulas are insufficient in organic chemistry, right? In general chemistry, you are always talking about molecules just using their chemical formulas. That's great for things like balancing chemical equations, but if we're trying to understand the chemistry of the molecule, we actually have to look at the structure. Alcohols and ethers behave very differently from one another. Even though they share this same chemical formula, they are not the same molecule. They have very distinct chemical properties, distinct reactions, all that sort of jazz. All right, just some terminology here. These two would be considered constitutional isomers. Because they got the same formula. But different structures. Okay. Now, Lewis structures you would have quickly graduated away from. We don't really like using Lewis structures, mainly because we're lazy and they take too long to draw. So instead, we're going to be using what we call bond line structures. Sometimes called skeletal structures. All right. In our bond line structures here, our carbons and our hydrogens are implied, but we do still have to represent all of our heteroatoms explicitly. So if I'm going to make a Lewis structure out of this molecule here, ethanol, I'm going to have two carbons, 1, 2, and my OH group. All right. My heteroatoms, I should say my heteroatoms and their hydrogens are explicitly represented in our bond line structures. So this is this same molecule, ethanol, just represented in this bond line structure. So everybody take a second, give me the bond line structure of our dimethyl ether here. I got my oxygen in the middle and my two carbons on either side here. All right, so let's make sure that we can interpret these bond line structures. All right, by that I mean I'm going to put down a bond line structure and you're going to tell me what that chemical formula is. And by chemical formula, I mean it's going to be something like CXHY. How many carbons, how many hydrogens are we looking at here? That's my question. so this first one here, what do we got? Who's brave? 6 carbons, C6, H14. All right, awesome. So just to be clear, our carbons are located at all of our endpoints and intersections, right? Endpoints and intersections. That's how we find our carbon atoms in our molecule. Our hydrogen atoms are also implied, and what we're going to do is just fill in to make sure that every one of our carbons has a complete octet. This carbon on the end here already has 1 bond explicitly represented. That means it must have 3 implied hydrogens. Right? Same with all of these on our endpoints here. This carbon right here has these 2 bonds explicitly represented. That means it needs 2 hydrogens to complete its octet. And then lastly, this one in the middle needs how many? Just 1. So that's how we get to our 14 hydrogens. All right, now we have these higher order bonds as well, whereas our normal single bonds are the sharing of a pair of electrons. A double bond means that there's 4 electrons being shared, or a triple bond means that there's 6 electrons being shared. All right, so what's our chemical formula for this molecule here? How many carbons do we have? Let's start there. 6. 1, 2, 3, 4, 5, 6. I will say this one right here, everybody loves to forget about. Remember, there's going to be a carbon on either side of our triple bond. Make sure you remember those 2 carbons. Okay, and then how many hydrogens do we have here? All right. So let's fill them in. 1, 2, 3. How many right here? Just 1. 5, 6, 7. How many on this carbon? 0. It's already happy. It's already got its complete octet. And my 1 on the end here, we need 1. Okay? Cool. All right, next we're going to remind ourselves, let's do the same game here, but also let's fill in any missing lone pairs. So chemical formula and any missing lone pairs. Okay, save this one for later. Oh, whoops. Fill in the missing lone pairs. All right, so how many carbons do we see? 4. We got 1, 2, 3, 4 carbons. All right, we have a nitrogen. A nitrogen should have how many lone pairs? We even made a cheat sheet up here. Just 1. How many should my oxygen have? 2. And then my halogen. Chlorine living in the same family as fluorine, being a halogen, will have 1 bond and 3 lone pairs. And then if I go in and I fill my hydrogens, how many hydrogens should I have? 8. All right, let's make sure we can see them. So this carbon on the end has 3. What about this one right here? It does need 1. Yep, we need to complete that carbon's octet. What about this one? It's good as it is. It's got its 4 bonds. This one on the end over here has 3. So then how did I get to 8? The one explicitly represented on that nitrogen atom. That takes me up to 8. Cool. All right. So now we're going to move on. Looking at this molecule here, let's remind ourselves we should be able to look at a molecule and look at each atom and determine its hybridization. All right, so I want everybody to identify all the sp hybridized carbons, the sp2 hybridized carbons, and then finally the sp3 hybridized carbons. All right, which ones are the sp hybridized? This molecule happens to have 2 of each. All right, so which ones are our sp hybridized carbons? About what type of bond? Are triple bonds. These 2 carbons here are sp hybridized. Those other 2 p orbitals, they are going into making these pi bonds here. All right, my sp2 hybridized carbons are the ones about my carbon-carbon double bond. All right, and then finally my sp3 hybridized carbons, these 2 here. They have all 4 bonding regions as single bonds. All right, and I kind of just gave the punchline away, but just to be clear here, what the heck is the hybridization? So if you remember back to general chemistry, you learned that you can pick an atom on the periodic table, and you should be able to tell me its electron configuration. That 1s2, 2s2, 2p2 business, right? Those are the atomic orbitals. When these atoms come together and they form covalent bond, they mix those atomic orbitals together, right? And that will dictate, amongst other things, the shape of those atoms. So an sp3 hybridized orbital means it took its s orbital and mixed it with all 3 of those peanut-shaped orbitals to make 4 new bonds, or 4 new bonding orbitals. If it's sp2, it took an s orbital and only 2 of those p orbitals, mixed them together. The leftover p orbital goes into making that pi bond. All right, so we also have this distinguishing types of bonds here. Single bonds we call sigma bonds. So these are all examples of sigma bonds. A sigma bond is kind of exactly what you would expect a bond to be. It means that the overlapping electron density is just sitting between the 2 atoms. Pi bonds are a little weirder. The electron density is pointed above and below. When we get to a double bond here, one of them is a single sigma bond. The other one is that fancy pi bond. All right, likewise, when we get to a triple bond here, again, one of them is a sigma bond, but the other two are those fancy pi bonds. Turns out that pi bonds are far more reactive than sigma bonds, which is why alkenes have a lot more interesting, alkenes and alkynes have a lot more interesting reactions than just alkanes. Alkanes are actually fairly boring in the grand scheme of things. Another thing that's important for the reactivity of those molecules is the geometry. So sp3 hybridized carbons, these have that tetrahedral geometry where all those bonds are spaced equally. sp2 hybridized carbons are much more accessible because they have a trigonal planar geometry. All right, and then our sp hybridized carbons, as I've drawn it here, I'm always good when we do our triple bonds to show that they are linear. So I didn't draw it in this checkerboard kind of fashion here, but rather drew it linear to that other bond. Okay, so reminding ourselves about hybridization and a little bit of a review of our geometry as well. Put those both in the same category. Okay, so going back to our bonding patterns here, we said that this is what we would expect to see for an element, how many bonds and lone pairs that element likes to have. So what do I mean by likes to have? Well, that means that this is the bonding pattern for an element when it's most stable. And an element is always most stable when it has a formal charge of 0, right? So by likes to have here, really what I mean is a formal charge of 0. And that's all well and good, but it turns out that a lot of interesting chemistry happens because molecules aren't very happy, because they're less stable. So we see a lot of interesting chemistry that occurs because molecules, or rather atoms, have a formal charge. So now what we're going to do is similar to our bonding pattern cheat sheet, we're going to make a few formal charge cheat sheets. So let's take a look. We're going to do oxygen first. What I'm going to do is I'm going to make another little chart here, but this time I'm going to include number of bonds. Actually, let's do formal charge first. Formal charge, number of bonds, and number of lone pairs. All right, and we will see oxygen in one of 3 different charge states. Won't ever really encounter it, at least not in organic chemistry outside of this pattern here. All right, well, the first one is what we've already discussed when it has 2 bonds and 2 lone pairs. That's in its most stable state, meaning that that oxygen has a formal charge of 0. All right, so let's just draw a little picture up at the top. Our oxygen with its 2 bonds and its 2 lone pairs. All right, so now I'm going to take one of those bonds away, and I'm going to replace it with a lone pair. All right, so now I'm talking about an oxygen that has just 1 bond and 3 lone pairs. What's that going to do to the electron density on that oxygen atom? I took this pair of electrons that it was sharing with another atom. I took that pair of electrons and I put it just directly on that oxygen atom. Is that going to increase the electron density or decrease the electron density? I took this pair of electrons that was shared and now it's sitting just on oxygen. Increase or decrease? What do we think? Who says increase? Cool. Who thinks decrease? Excellent. So yes, it will increase the electron density. If we have a lot of electron density, what would that be? A positive or a negative formal charge? Negative, right? Electrons are negative. So if we take one of those bonds and make it into a lone pair, that means we're giving oxygen a negative formal charge, a formal charge of -1. And if we're drawing that oxygen, we got to be good and include that formal charge on there. All right, so replacing a bond with a lone pair increases electron density. What if I do the exact opposite and I take a lone pair and make it into a bond? So now my oxygen has 3 bonds and 1 lone pair. All right, what's that going to do to our formal charge? It's going to increase it. So this would be oxygen with a formal charge of +1. Right, now we've decreased the electron density on that oxygen atom, creating a positively charged oxygen. All right, so this is our formal charge cheat sheet here for oxygen. We're going to play the same game with our other heteroatoms as well. All right, so let's do one for nitrogen now. Let's see if I can just squeeze it in here. Sure. This won't bother me if it looks ugly. Okay. All right, so nitrogen, we said if we're going to put formal charge of 0 in the middle, that's when nitrogen likes to have 3 bonds and 1 lone pair. It's nitrogen in its most stable state. Doesn't necessarily have to be hydrogens. All right, I want everybody to take a second. Based on what we just did with oxygen, fill out this table for nitrogen. All right, fill in these next 2 columns here. All right, so again, similar logic. We're going to replace a bond with a lone pair, and that's going to what? Increase electron density or decrease electron density? Increase electron density, which is why we would have a negative formal charge on this nitrogen here. Nitrogen, super pissed off with this negative formal charge here. Very rarely do you actually see these, although they will come up every once in a while, but they're very, very unstable. Very strong bases. More commonly, nitrogen will donate that lone pair and turn it into a bond, giving it 4 bonds and 0 lone pairs, meaning that it will have a +1 formal charge. Okay. We're going to do another one here for our halogens. All right, but I'm going to make you all complete this one on your own here. Again, we said fluorine, an example of a halogen, likes to have 1 bond and 3 lone pairs. And you guys can complete the rest of this chart on your own here, exactly as we've done for our previous 2 heteroatoms. Okay, I'm going to have you all do that one on your own. The one that we're going to do together here is actually the star of the show, carbon. And carbon's is a little unexpected. At least part of it is. So first of all, we put carbon likes to have 4 bonds and no lone pairs, meaning it's got that formal charge of 0. All right, everybody take a second and fill in this -1 column for me. This is what we would expect based on all the other trends that we've seen. All right, so again, we're going to turn one of those bonds into a lone pair. So now we've got a carbon with 3 bonds and 1 lone pair. Minute that negative charge. Because this is carbon, we got a special name for these types of ions here. All right, when we see carbon with a negative charge, which isn't terribly often, it's very unhappy, but this we call a carbanion. Right, remember, anions are those negatively charged ions, so a carbanion is a carbon with a negative charge. All right, but this last column here, carbon with a +1 formal charge, is one that we see quite often, but it's going to break all these trends that we've been seeing up until this point. Right? First of all, we can just note, previously what we were doing was we were taking a lone pair and turning it into a bond. Well, we can't do that here, right? We don't have any lone pairs to work with. Okay? The other thing that I want to note about all of these heteroatoms is regardless of their formal charge, you can notice that they always have a complete octet. Oxygen, nitrogen, the halogens, you will never see them with a broken octet. If you're ever drawing just 6 electrons around one of those atoms, you're doing something wrong, all right? Even when it has this formal charge of -1 or +1, it's got a total of 8 electrons in its valence shell, right? So we didn't break its octet by forming these different formal charges. Carbon's going to be unique in that respect. So first of all, if we're going to have a carbon with a +1 charge, that means it only has 3 bonds and no lone pairs, meaning it only has a total of 6 electrons, giving it an incomplete octet. Okay, and because it has an incomplete octet, these are indeed unstable, but we still see them quite frequently, usually just as intermediates in a reaction, right? So something that's very short-lived, very high energy, but really important for the chemistry of that molecule. We have a special name for these as well, whereas the negatively charged carbons are carbanions. This would be a carbocation. All right, so again, when we say an element likes to have a certain bonding pattern, that means it has a formal charge of 0, which means that it's the most stable, right? Not a lot of interesting chemistry happens between two super stable molecules though. So oftentimes formal charges are involved in our chemical reactions, and so we've broken it down based on family here, the bonding patterns that we would expect to see for those various formal charges, okay? I'm going to also note here, part of your review is going to be reviewing functional groups and nomenclature. All right, for function, and these are two things that I'm going to leave for you to do on your own. All right, first of all, pretty straightforward to look up different functional groups. If you don't remember, we have to have our functional groups known. I will note that you have this free online textbook that we're using this semester. There's no cost associated with the textbook. It's a PDF that you download off of Canvas. It's under our course introduction module. All right, if you look in that textbook at chapter and section 3.1, that's when it will go over functional groups. All right, so if you need to review, you can check there. Nomenclature. What I'm going to do for nomenclature in terms of review is I'm going to expect you to know alkane nomenclature as well as cyclic alkane nomenclature. All right, you would have also discussed alkene and alkyne nomenclature. One of the first chapters that we're going to do in this course is going to be on what are called conjugated dienes. We're going to basically revisit alkenes, and that'll be the time that I think that we can revisit nomenclature for alkenes. All right, so for right now, what I expect you to know, and alkane nomenclature is really just the basics. Our rules that we need to know for naming these molecules are very most basic nomenclature rules. All right, so this is, I'm going to expect you to have reviewed on your own here for this week, our nomenclature and our functional groups. All right, nomenclature is something that every new functional group that we'll discuss will also discuss nomenclature for it. People tend to do really well on nomenclature because it's the same frickin' set of rules over and over and over again. All we're going to do is introduce a new suffix, maybe a complication or two here or there, but it's just rinse and repeat as we go. So as long as you have these basics down from the first semester for alkanes and cyclic alkanes, we should be good. All right? And I'm going to kick that for y'all to do on your own because I want to spend a lot of time on what I feel like is the weak point that I see for students coming into my Organic Chemistry 2 class, and that revolves around reaction mechanisms. All right, so our electron pushing arrows, we want to be really good at our reaction mechanisms. I think that a lot of students treat reaction mechanisms, those arrows, as something that you just got to memorize. And that works great when you have like one reaction mechanism to learn. We're going to get to the point where we have quite a few of them. And if your goal or if your plan is to just memorize arrows, it's going to fall through really quickly. We need to sort of get better at seeing who our nucleophiles are, who our electrophiles are, like looking at a reaction, looking at two reactants, and being able to predict what we think is going to happen, not just have stuff memorized, right? We want to be able to understand this stuff, not just try to regurgitate from memory, because there's going to be a limit on how much we can do if our plan is to just memorize, all right? So what we're going to do is spend the rest of this class period and next class period talking about reaction mechanisms. We're going to start from the beginning. A lot of our reactions in organic chemistry are what are called polar reactions. All right, polar reactions are reactions between nucleophiles and electrophiles. everybody just loves the sound of my voice saying nucleophiles and electrophiles, because holy heck, are we going to be repeating this over and over and over again this semester. All right, so let's just kind of review what the heck I mean by nucleophiles and electrophiles. All right, so first of all, our nucleophile in a reaction. So a molecule is playing the role of a nucleophile. All right, if we just kind of want to break this word apart here, the nucleo stands for the nucleus of an atom. What particles live in the nucleus of an atom? Protons and neutrons. And the protons are really the important ones, right? Because those are the ones that are charged. They have that positive charge. So we have this suffix phile on here. What does that suffix phile mean? Loving. So specifically the phile part means loving, right? So nucleophile, this would be a species that loves that positively charged nucleus of some neighboring atom. All right. In order to be a nucleophile, something that loves positively charged species, that means that it itself has a lot of electrons, right? So our nucleophiles are always going to be our electron-rich species. All right, they're electron-rich, and most importantly, in the role of this polar reaction, they're always going to be donating a pair of electrons. All right. The other role is played by our electrophile. What do electrophiles love? Negatively charged electrons, right? So we got that same suffix phile. So an electrophile is something that loves those negatively charged electrons. Right, so our electrophiles, the reason why they love electrons so much is because they themselves are electron poor. All right, and a very important caveat of something being able to be an electrophile. Not only does it have to be electron poor, it also has to be able to accept an electron pair. And that's actually a pretty stringent criteria. All right, we'll see why here in a second. All right, so vast majority, there's exactly one that I can think of that does not fall under this category of being a polar reaction that we're going to, I should say that. Yeah, maybe. Fall into this category being a polar reaction that we're going to study in this course. Polar reactions take place between nucleophiles and electrophiles. So one of the things that we're going to do when we're trying to predict reactions is say, all right, what's my nucleophile? What's my electron-rich species? Okay, what's my electrophile? What's my electron-poor species? And what do nucleophiles do to electrophiles? They attack. All right, so we say nucleophiles will attack electrophiles. And really what we mean by attack is they donate their electron pairs. All right, but once we've identified our nucleophile and our electrophile, we're in business. Then we can start predicting what's going to happen in our chemical reaction. Okay, so let's talk about different molecules that would fall under these two categories here. The ones that I think are the easier to identify are the nucleophiles. So let's start there. All right, so our nucleophiles, again, let's just remind ourselves, these are our electron-rich species in our chemical reaction. We see a lot of the same atoms playing the role of a nucleophilic site, the actual atom that's doing the attacking in our molecule. All right, a lot of our heteroatoms are very happy to be electron-rich. So oxygen, we will very often see playing the role of a nucleophile. This could be something as simple as the hydroxide ion or a negatively charged oxygen on an organic molecule. Okay. Some terminology, again, we know this one all the way from general chemistry. From the very first semester, we made you identify this guy, hydroxide. Right, hydroxide, your first strong base that you were ever introduced to in the world of chemistry. These things here would be if I took an alcohol and I removed that hydrogen from it, I would create a negatively charged oxygen on an organic molecule here. Whereas this is a hydroxide, this is an alk oxide. Because it's got some alkyl chain on it, some number of carbons and hydrogens on there. We will talk about alkoxides quite frequently, so a term that it's good to have in the back of your mind. Oxygen's good at being a nucleophilic site. Sulfur is also really good. Sulfur not quite seen as frequently because it's not as common in nature, but nonetheless is a very good nucleophile, in part because it's a lot larger than oxygen, but same idea, same family, so same bonding patterns. We could just have this hydrogen sulfide ion or a deprotonated thiol here. Both of these would be examples of good sulfur nucleophiles. Crunch this together. All right, nitrogen. Again, not quite seen as frequently, but we will see it every once in a while, a negatively charged nitrogen. So that's either like a deprotonated, two of them, ammonia molecule, or could have it again with some alkyl chain on there. All of these would be examples of very good nucleophiles, good strong nucleophiles. And they're strong nucleophiles because they're very electron rich. What's it that's giving it away, that's making it super obvious that these are strong nucleophiles here? Not just the lone pairs, but the formal charge, right? So not only, lone pairs are essential. You can't be a nucleophile without lone pairs. But these are extra good nucleophiles because they have that net negative charge, right? Okay, we can also put our halogens, or more specifically our halide ions, All right, if we have a halogen that has that net negative charge, all right, when you fill out your bonding pattern, you're going to take that bond and turn it into a lone pair. So that means we have all lone pairs on a fluoride ion or a chloride ion, bromide or iodide. These are all great. All right, and then every once in a blue moon, we will see carbon playing the role of a strong nucleophile. There's really only a set number of examples, and negatively charged carbon is really hard to come by. So you really only ever see that if it's in a very high order bond, if there's a triple bond associated with it. So the one that we'll see the most frequently is our cyanide ion, carbon triple bonded to a nitrogen. All right, the presence of that nitrogen stabilizes that negative charge, so we will see these nucleophiles quite frequently. The other one that you don't see quite as frequently, but we're going to note it because it was noted last semester, we know how to do it, is if we take this terminal alkyne and we remove the hydrogen from the very end here. So we have this super strong base that we can use to remove a hydrogen from the end, creating that negatively charged carbon at the end of our triple bond. All right, so these are all these strong nucleophiles here, right? And again, our heteroatoms are really good at playing the role of these nucleophiles, these strong nucleophiles. They're more stable with these negative charges. Carbon we'll see playing the role of a strong nucleophile every once in a while in these very specific cases, right? Where that negative charge can be stabilized by that higher order bond. All right, so those are our strong nucleophiles. Those are the easiest ones to spy. We could also have weak nucleophiles. Okay, what's going to make these weaker is that they have a net charge of 0. All right, so no net charge. Importantly, any weak nucleophile, any nucleophile period, they still must have lone pairs. Right? Remember, one of our requirements for a nucleophile was this ability to donate an electron pair. So even our weak nucleophiles, they have electron pairs to donate. All right, so just to give some examples here, one weak nucleophile we'll see quite often would be water. Okay, and it can be either, the simplest oxygen or put some alkyl chain on there. So we'll see alcohols playing the role of nucleophiles. Okay, same with sulfur. Sulfur is actually quite a good nucleophile, again, just because it's really large. Its electron cloud is really large and spread out, so it can donate those electrons a little bit easier than the smaller atoms. All right, our nitrogens, same deal. Okay, so again, those same nucleophilic sites that we saw before, oxygen, sulfur, nitrogen. We're going to note that we don't have any neutral halogens on this list here. Halogens, when they're neutral, halogens are just very electronegative, so they're not really keen on sharing their electrons unless they have this net negative charge. And carbon, we're going to see, doesn't have any lone pairs. There is one important carbon exception that we are going to put down. This is actually the first nucleophile that you ever really took a close look at in Organic Chemistry 1. And that is our alkenes, our carbon-carbon double bonds. That pi bond, because of the geometry of this molecule, as well as the geometry of that pi bond itself can be a donatable pair of electrons. All right, so that second bond in our alkene is going to play the role of a nucleophile. All right, so here's sort of our little cheat sheet. By no means exhaustive, but just kind of giving us a head start in terms of being able to identify nucleophiles and electrophiles. Here we have a list of nucleophiles broken down by our strong nucleophiles, those with these net negative charges, and then our weak nucleophiles, those that have this neutral charge, but still have these lone pairs, or in this special case, pi bond that can be donated. All right, electrophiles are a little bit weirder, a little bit harder to spy. Good news is that there are way fewer of them. All right, so we're going to put these into categories here, our different electrophiles. The first one, kind of the best and easiest to spy, are carbocations. All right, so if I just want to draw a carbocation, again, that means my carbon has 3 bonds and no lone pairs. So I'm going to give it that positive charge. And whereas nucleophiles were electron rich, electrophiles are electron poor. So what's going to give it away here that this carbocation is such a good electrophile? It's got that positive charge, right? Definitely an electron poor atom. But a positive charge isn't enough to signal where my electrophilic site is, because there's something equally as important as being electron poor, which is the ability to accept pairs of electrons. All right, and that isn't always the case just because you have a positive charge. Carbocations, though, are an exception. Carbocations can accept electron pairs, and that's because they're that one type of formal charge that has an incomplete octet. So they are very happy to accept a pair of electrons in order to complete the octet of that carbon atom. Okay, but I want to put down a caution here. So now we're just going to make a note here. Not all positive charges are electrophilic sites. They will not be electrophilic sites if they cannot accept electron pairs. All right, so let's give a simple example here. The hydronium ion, very important molecule that you would have spent a lot of time discussing, especially in Chem 1B. This molecule is an electrophile, but just not at the site that you would think, just by looking at it. Because if I'm looking at this molecule here, the formal charge of +1 resides on what atom? The oxygen. All right, but what's the problem? Let's say that I was some nucleophile, and I'm trying to donate a pair of electrons to this oxygen here. What's the problem? It already has a full octet. It can't accept any more electrons. You're not going to find oxygen with 10 electrons in its octet. That's not going to happen. So this cannot accept any more electrons. Because it has a complete octet. Okay, so just because an atom has a positive one formal charge doesn't mean that it's going to be our electrophilic site. It does help us recognize that this will play the role of an electrophile. It's just not going to be at that oxygen atom. And so this takes us to our next important category, and this is going to be really important to just keep in mind. Acids are electrophiles. All right, one phrase you're going to hear me say over and over and over again. Acids are electrophiles. So let's take our, and I'm going to complete this thought here in a second. So let's just take this same example here, our hydronium. All right. We said that this oxygen can't be our electrophilic site, right? It can't accept any more pairs of electrons. So then what's going to be the electrophilic site in this molecule here? If it's not the oxygen, we only got one other choice. It's going to be the hydrogen, all right? Acids are electrophiles at their donatable hydrogens. Remember, in order to be an acid, that means that you can donate a hydrogen. Donating that hydrogen is playing the role of an electrophile. Okay, so here is my electrophilic site. If I had some base, that base can grab that hydrogen kicking off that water molecule as a leaving group. All right, and that takes us to our next category, and we will start this next class period and sort of add on to this. But our next category, electrophiles, good electrophiles will often have leaving groups associated with them. Things that we can kick off that are nice and stable all by themselves. So for example, in this reaction here, when my base accepts this proton, we kick off a nice, stable, neutral water molecule. All right? We will finish up this next class period, and then we'll start getting into these electron pushing arrows. I kind of put some down here, but we'll lay down our rules, make sure we all understand how those arrows work. All right? As I said at the beginning, make sure you take your daily quiz by the end of the day. We will be starting each class period with those daily quizzes. They'll open 5 minutes before class starts, and they'll be due 5 minutes after class starts.